Hello, honors pre-calculus students. This is Mr. Hazelhorst coming to you live from room A08. I want to take some time today to talk to you guys about exponential functions and their graphs. And this is going to be serving as our introduction lesson to Chapter 3. We'll be focusing here on Chapter 3 on both exponential and logarithmic functions. We will be doing some more graphing. And so that's going to be important to know up front as we get going. But today we're just simply going to focus in on exponential functions. So let's start out with a little definition and example of what an exponential function is. All right, so an exponential function is any function that takes on the form f of x is equal to a to the x power. Now it's not key that it's a, it's just representing any base that's positive. All right, so that's important to make note of, is that our base is a positive value and that a cannot be 1. Now, the reason why a cannot be 1, pretty simple. If we think about the number 1 and we raise it to any power, doesn't matter what it is, right? What's a to the second power? We know it's 1. What's a to the millionth power if a is 1? Well, you know it's 1. So the key here is that we need to have some other value, okay? Now, I should make note when we say that a needs to be greater than 0, I do need to clarify the difference between these two functions. So if I have f of x is equal to a negative 2 to the x power, okay, that would still be considered an exponential function, right? Because the base in this problem is 2. Right, I'm raising 2 to the x power. Think about order of operations, right? Exponents come first, and then I apply the negative sign. So the negative sign in this example is representing a reflection. Right, now we need to contrast that with f of x equal to a negative 2 to the x power, okay? Now what happens here is when I take a negative 2 and I put it in parentheses, well, we change the order of operations, right? So now what happens is that means whatever's inside the parentheses, well, that gets raised to the power. And we have something completely different here. What happens if I have a negative 2 to a certain power, right? Think about negative numbers. If it's an even power, it becomes positive, and if it's an odd power, it becomes negative. So it becomes this function that bounces up and down between positive and negative values, and that's not what we want to have here, all right? So that's the key to understand when we say that a has to be greater than 0, all right, is that we're focused on the base of that function, okay? Now, we do need to make note as well that f of x equals x cubed is not an exponential function. While it has an exponent in it, it's not considered an exponential function, right? This would be a polynomial function like we dealt with in Chapter 2. The key is that the variable x has to be in the exponent. And that's the difference between f of x equals a to the x power and f of x equals x cubed, is the position of the variable. All right? So let's get into a little bit about the characteristics and what the graph looks like. And this would be an example of an exponential function, right? We have y equals a to the x power. A couple things that we want to make note of here is that the domain, right, is negative infinity to positive infinity. The range is from 0 to infinity. All right, the x-axis is actually serving as a horizontal asymptote. Okay, so if I take any number and raise it to a power, right, it doesn't become negative, all right, unless I put a negative sign out there. But in the parent function, right, we're assuming that base is positive. The intercept, y-intercept specifically, is the point 0, 1. Right? And the reason for that is if we take any number to the 0 power, it is 1. All right? That's why our intercept is where it's at. And this function is constantly increasing from left to right. Okay? Now we can compare this function with its reflection. All right? So if we compare it to this function, which all we've done is we've made the variable now negative. So it's a to the negative x. Right? And we reflect that then about the y-axis, okay? And you've worked with these graphs before. These aren't anything new. You might remember that we call anything to the positive value, we consider this exponential growth. and we consider the other graph exponential decay. All right? And the reason for that is the graph on the left side is constantly increasing, it's growing, while the graph on the right side, as we read it left to right, is constantly getting smaller, and it's decreasing. Okay? Now, a couple of things to make note of is that with regards to the characteristics, really nothing changed except for the fact that the graph is decreasing. It still has the same domain and range, it still has the same y-intercept, and it still has the same horizontal asymptote. All right? So let's do a little practice with graphing here. So we want to think about our parent function, all right? F of x is equal to 4 to the x power. All right, we're going to graph it, and we're going to comment on any key characteristics of the graph. So first off, I want you to think through what are the transformations that are occurring here to our exponential function. And we need to go back to what we learned in chapter 1 with regards to transformations, right? Are there any reflections in this problem? Are there any horizontal shifts? Are there any vertical shifts? So those are all things that we want to take into consideration, okay? And so in this problem, we can see that we have 3 different transformations occurring. And so let's just make note of those before we jump into the graphing of the function, okay? All right, so our transformations to begin with, okay? The first thing as I read through this function, I'm not going to worry so much about the number 4 because all this is representing is my base in this problem, okay? But it doesn't impact much of my graph. You know, if I was creating a table of values, it would, but we're not going to worry about a table of values. We're just going to transform the parent function, okay? So I don't have to worry about the base, all right? But I do need to make note of the negative sign that's in the exponent, okay? That negative sign in the exponent is going to cause a reflection about the y-axis. And then we can see that we have 2 shifts occurring in this problem, all right? We have a shift right of 2 units. And we have a shift up of 3 units. And so both of those items we want to make note of, okay? Now that I've mentioned my transformations, it'd be very easy for me to graph this problem, right? Now, what I'm going to utilize is think of my parent function, right? We know that our parent function has a horizontal asymptote of the x-axis, right? Well, that horizontal asymptote is going to be impacted by my shift up of 3 units. So that's the first thing that I'm going to sketch, is I'm going to change where my horizontal asymptote is, okay? Now it'd be nice to have a couple of points to help us graph this. And I'm really just going to utilize 2 points. I'm going to first off think about where was the y-intercept originally on the parent function. Well, originally on the parent function, the y-intercept was at the point 0, 1. Okay? Well, that point is going to be impacted by both of our shifts. And so I'm just going to shift that point accordingly. So we're going to shift right 2 units, and then I'm going to shift up 3. So here is my new, I'm going to call it y-intercept. That was the y-intercept of the parent function, but it's no longer intersecting the y-axis, right? Now it's kind of sitting off in space, but it's in the same relative position to the horizontal asymptote. The second point that I'm going to utilize, and it's one of my characteristics of the graph, so it's helpful for me to find anyway, but I'm going to look at the y-intercept, right? What happened to the y-intercept? Where'd it go? Okay, well, we know the y-intercept is very easy for us to utilize. We just need to plug in 0 for x. So if I go back to my function and I plug 0 in for x, well, what I end up with there is I end up with 4 to the negative 2 power, right? Plugging in 0 for x. So I end up with 4 squared plus 3. Well, 4 squared is 16 plus 3. My y-intercept is now at the point 0, 19. Now that's way off of my graph, but that gives me an idea, right? That point is way up off of the slide. So when I'm sketching this, right, I know that in terms of what I see on this little piece of graph paper, it's not going to cross the y-axis, right, because it doesn't cross until point 19. We've got the shifts taken care of. The other thing that we need to take into consideration is the reflection. All right, and this function is representing an exponential decay instead of an exponential growth. So that means this function should be coming down. Right, so I'm just going to draw this. I'm going to come way up here. Right, I'm not crossing my y-axis. It's going to be somewhere close to that. I'm going to pass through my transformed y-intercept and then continue along my horizontal asymptote. And so my function of my exponential function is going to look something like this. Okay. Now notice we didn't need to plot a table of values. Right, we looked at our transformations. We found our new y-intercept, and that was enough information for us to sketch the graph. Okay. Now let's comment on a couple of key characteristics. Right, we have our y-intercept identified already. We already applied the transformation to the horizontal asymptote, so we can go ahead and make note of what that is, right? Our horizontal asymptote is sitting at the line y equals 3. And then the only other things that we need to really mention are the domain and range. Okay? Well, the domain of any exponential function in interval notation would be negative infinity to positive infinity. We really have the right to plug in any value into the function. And the range is going to be impacted by the shift here as well. If I just analyze the graph, the lowest that this value is going to, or this function is going to get to is 3. Now it's not actually going to touch it because it's a horizontal asymptote. So our range would be from 3 to positive infinity. Even though this function is going down, right, as it moves, as I look towards the left, it is increasing infinitely, okay? And so if I ask you to graph an exponential function, those are going to be things that I'm going to look for in your graph, okay? Can you recognize the transformations, apply them correctly? Can you identify a y-intercept and a horizontal asymptote? And can you identify the domain and range? And if we can do those things, we're going to be in good shape, okay? All right, well, moving along here, let's talk next about the one-to-one property. This is a very simple property to apply when it comes to solving equations that involve exponents. Now, this property doesn't always work, but the key to it is, can we rewrite problems so that both sides have the same base, okay? So let's start out with our problem 1/3 to the x power equals 81. And the question that I have to ask myself, is there a common base between 1/3 and 81? And hopefully we recognize that, yeah, there is. Both of these can be represented with a base of 3, okay? So that's essentially what we're going to do, is we're going to rewrite them so that they have the same base. So let's start out on the left side of this equation, right? We're going to end up with 3. Now, if I want to move that 3 up, what does that take? Think about what you know about exponents, right? Hopefully you remember that's going to require a negative exponent, right? So 1/3 to the x power is the same thing as 3 to the negative x power, okay? Now let's do the same thing with 81. How can I rewrite 81 with a base of 3, right? 3 to what power is 81? Well, you might have to do a little experimentation here. And we can think about, we know 3 squared is 9, 3 to the 3rd is 27, 3 to the 4th, well, that's 81. And here's where the one-to-one property kicks in. All right, if I have the same base, all right, what that means is if the bases are equal, then the exponents have to be equal. So to solve this, I can essentially drop the base, and I can just rewrite this equation saying, okay, I've got to have equal exponents in order for this function to be equal. All right, so I can say a negative x has to equal 4, or simply x has to equal 4. All right? Excuse me, negative 4. Let's make sure we get that negative sign in there, okay? So again, that's the use of the one-to-one property, okay? Now that also applies in our second example. Now the nice thing is here, we don't have any rewriting to do in this problem. They both have the same base. They both have the base e, right? So if both of the bases are the same, again, essentially we can drop the base and we get 2 times x, equals x plus 2. And we just solve it. Subtract x from both sides, and we end up with x equals 2. Now, the reason why I utilize that example is not because it was a difficult example, but this example brings into play a very important number in mathematics and for us in this chapter, and that is the natural base e, okay? So e is known as the natural base, and it's one of the most important bases used for exponential functions. It shows up in a lot of different equations that model the real world. All right, e is known as an irrational number, meaning it can't be written as an exact value. It's like pi. It's an infinitely non-repeating decimal. It's approximately the value 2.718281. Okay, so e is just what we use to represent it, just like we use the pi symbol to represent approximately 3.14159, blah, 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 right? All right, so e is a number that you're going to see a lot, okay? And we want to be aware of that, that when you see e in this chapter, it's not a variable, right? It's not representing some unknown. E is representing a known value. It's a number, just like pi, okay? So here's our first example of when e shows up, all right? You've worked compound interest form problems before in other classes. And so this is an example of where e shows up. So here on this slide, we have two different types of compound interest. We have on the left side, if we are compounding some sort of money account, savings account, investment account, so on, and it's compounded a certain number of times a year, okay? So we can go through all the variables there, right? P is a principal. What's the amount of money that you're starting with? N is how many times does it compound a year? So if it's quarterly, it will be 4 times a year. If it's biannually, it would be 2. Something along those lines. All right. The rate will represent as a decimal, and the time is representing time in years. Okay. And then we also have the equation PERT, right? Equation most of you are probably very familiar with, and so we see some of those same variables, but we do see that natural base e show up in this equation. This is used in our continuous compound problem. So let's take a look at a couple of examples here. All right. So let's say we had $12,000 that we just happened to stumble upon. That would be nice, right? I think all of us could use $12,000. Now, many of you are probably thinking, if I had $12,000, what would I spend that on? But it is wise to save some money. So let's say you made a wise, mature, adult decision and said, you know what, I'm going to invest this $12,000. Essentially, I'm going to let my money work for me instead of me working for my money. And so I invest it at an annual interest rate of 9%. Now, I will tell you, if you can get an annual interest rate of 9%, you take it, you run with it, you lock it in. That's pretty solid, all right? So ultimately, that's probably a bit of an exaggeration, but we'll use it for this example nonetheless. And let's say we wanted to find the balance after 5 years. And we're going to look at this 2 ways. What if it was compounded quarterly, meaning it was compounded 4 times per year? And then we'll also look at what if it was compounded continuously. And if you have your graphing calculator handy, you might want to pull that out, because we are going to let our graphing calculator run the actual calculations for us. We'll just set up the work, type it in, and let magic happen. All right. Well, let's focus in on the quarterly part first, okay? So if we look back at our notes, or on that previous slide, we know that the equation for compounding a specific number of times is A equals P times the quantity, 1 plus our rate divided by n raised to the n times t power. Okay? So let's just fill in what we know about this problem. All right. So our principal amount, the amount of money that we're beginning with, is $12,000. All right. We're going to continue to fill in what we know about this problem. So our rate is 9%. Now, very important here, we want to represent our rate as a as a decimal. Okay. So our rate would be 0.09. And we're going to divide that by n, the number of times that it compounds per year, which is 4. And then we'll take this and raise it to the 4 times our time, which in this problem is 5. Okay? And so now the fun part is typing this into our calculator. And this is pretty simple to do. Let me pull up my calculator so I can walk us through this. All right, so we're just going to type in exactly what we just wrote down. So 12,000. I'm going to throw in a parenthesis, 1 plus my rate, 0.09, and then I'm going to divide by time, or excuse me, my number of compoundings, which is 4, close my parenthesis. and then I'm going to raise it. Now, to raise to a power, I need to use my exponent button, which is over here on the left side, or excuse me, the right side of my graphing calculator. So that little caret key, we're going to press that. Okay. Now, you'll notice my graphing calculator actually superscripts the exponent, but some of you have older models of calculators where it just puts the arrow on there instead. And what you're going to want to do is you're actually going to want to put a parenthesis after that, because we need the n and the t value to both be represented in the exponent. Okay? And so on my calculator, it works out really nice because, again, it's superscripted. So I'm just going to simply plug in 4 times 5. Okay. Now, for those of you who don't have the superscript, the reason why we want a parenthesis there is if we don't include a parenthesis, your calculator is programmed very well and it will follow order of operations, which means it will raise to the 4th power and then multiply by 5. Well, we want the 4 times 5 to happen first. So we need to have that within some grouping symbols to bump it ahead of the exponent order of operation. All right. But now we can just press enter. And we can see if we had a 9% annual interest rate and we were compounding 4 times per year, we would make over $6,000 in a 5-year period by doing nothing but letting it sit in an account. Now, that's pretty awesome. Again, probably not the most realistic, but it does show the power of exponents. All right, so our amount of interest here. All right, not our amount of interest, but our total amount now was $18,746, or excuse me, $26. Trying to go off of memory here. $18,726, and I think it was 11 cents, if I remember correctly. All right, now let's look at what would change if this was compounded continuously. So now we're going to utilize our PERT formula. So our amount of money would then be figured by our principal times our natural base raised to the RT power. And so if we plug in our values there, our principal again is $12,000. We have the natural base, and we're going to raise this to the 0.09 times 5 power. All right, so again, let's pull out our calculators, type that in. All right, so we got $12,000. We do have a natural base button on our graphing calculator. It's found over here on the left side. If you locate the LN button, it is written up above that. So to access that, I have to hit my second and then hit my LN button, which stands for the natural logarithm. We'll talk about that later on. And again, most calculators, you're going to see an E, and then if it's like my model, it will superscript. Some of you with older models, you're going to see the caret symbol and then a parenthesis. So your calculator is recognizing, okay, you're probably going to put something in the exponent here, so we're going to put a parenthesis so that we make sure we get everything up there that we need. All right, so I'm just going to go 0.09 times 5. Hit enter. And so if we compounded continuously, we make almost an extra $100 over the course of a 5-year period. Because again, it's compounding more often, compounding continuously. Okay, so let's get that work written down here. So our total amount here then, if I remember correctly, was I think $18,819.75. I hope my memory is serving me well there. If I'm wrong, you guys can fix that. But that's an example of how we utilize those compound interest formulas. And I know it's something you've done before in Algebra 2, but I wanted to take the time to walk you through that again. All right, well, I know that you do not have this slide on your handout, so you might want to take a moment to write your homework assignment down. If you guys have any questions over this, we will have time to address those in class, and so just kind of mark anything on your notes that you want to see explained further. I do want to make note on your homework assignment here that there's some problems with some asterisks. In the directions of your textbook, it asks you to use your graphing calculator. However, I want you to graph those without your graphing calculator because that'll be the expectation when we take your quiz and test over this chapter. So it'd be wise to practice without that. This video is posted online on my classroom website, so if you decide later on you need to go back and kind of rewatch something, or I went too fast over something, just know that you can access that online. All right, thank you for your attention. I hope you guys have a fantastic day, and I will see you soon.